Kirchhoff's current law states that the algebraic sum of the currents entering and leaving a junction of a network is zero. The first equation states that the total current at a node must equal to zero when considering the magnitude and direction of the individual currents. The second equation states that the current flowing into a node must always be equal to the current flowing out of the node. So, in order to understand the theory, we must disintegrate the concept. Current, resistance, and nodes are the main components that make up KCL. Current is a charge through a point per second, or 1 coulomb per second is an amp. Current is considered the flow of electrons which contain a charge. A resistor is a two-terminal electrical component that implements electrical resistance as a circuit element. In electronic circuits, for our case, resistors are used to reduce current flow. A node is any point on a circuit where the terminals of two or more circuit elements meet, or can be simply said, a junction. The flow of water can be used to extensively explain KCL. This concept is called the water analogy. The diagram on the left represents how the flow of water at Q1 spreads into Q2, Q3, and Q4, which represents the flow of electrons at a junction. It is visible that the volume of water in Q1 divides into Q2, Q3, and Q4. The diagram on the right represents how the resistance affects the flow of water, which represents the flow of electrons. It is visible that high resistance allows lower flow, while low resistance allows higher flow. This simple example shows how to use KCL to calculate the current I3. According to KCL, total current of 60 mA should equal to the sum of currents divided among the separate branches, which gives the value of 25 mA for I3. This problem, which is a little more complex than the previous one, can be used to prove KCL. In this example, I1 and I2 is calculated using Ohm's law, which is 3 amps and 2 amps respectively. And then the answers for I1 and I2 is used to calculate IT, which is the sum of the two currents in separate branches according to KCL. To prove that the answer is valid, the total resistance of the resistor set up in parallel is used in Ohm's law with the source voltage, which results in the same answer as KCL.